Page 2, some more balancing. When I see a combustion reaction, I always have the same strategy. I make my chart with C's, H's, and O's, and I fix them in that order. I count up the both sides. I see 6, 6, 2 versus 1, 2. 2 plus 1 is 3. And I don't recount. I just first fix the C's. I put a 6 there. That will change this to 6. Now fix the H's. I put a 3 there to get 6. Now count the oxygens because I just changed both. I have 6 times 2 is 12 plus 3 equals 15. So I like that we have one of these. This is the classic combustion. One of two things always happens with a combustion. You either get to the point where you fix your C's and H's. When you count it up, you either write something there that fixes everything and you're done, or you're going to have an odd and an even number on each side, and then you have another step. We have an odd and an even. If I have 2 on this side and 15 on this side, an odd and an even, there's nothing I can write here on the O2 that will get her done. Well, there is. I suppose I could write 7.5, but that's not legal. So that what I would have to do is to scale. It's because we can't have a half of an O2. They come in O2s and not in O's. So instead of 7.5, we need to scale everything up. So I'm going to go and double everything. Instead of one of these, I'll have 2 of these. Instead of 7.5, I'll have 15. Instead of 6, I'll have 12. Instead of 3, I'll have 6. That one is done. When I have an odd even, if I go double everything, it will make it so that there's something I can write on the O2 line to get her done. Next one's another classic. It's a double replacement reaction, and in this type, keep the polyatomic ions together. I'm not going to count H's, S's, O's, and BA's. I'm going to count H's, SO4's, BA's, and OH's. And on this side, so it looks like I don't have H's and OH's, but I'm going to. I'll show you what I'm talking about. H's, SO4's, BA's, and OH's. I like to write it the same as the left, so I can just go down the line and compare H's first, SO4, so I can kind of go down the line. When I count this up, I see 2 of these. Whoops, sorry. I see 2 H's, so that goes down here. Only 1 SO4 at this point, only 1 BA, and 2 OH's. And this side, it would look like you don't see. It look like there's a 2 here, but careful. I look at this H2O in a double replacement as an HOH because of practice. Hopefully you've practiced. When I count it that way, I see 1 H, 1 OH, 1 BA, and 1 SO4. This then just makes it relatively easy to see that it's only the H's and the OH's that don't match. So all I have to do is double this, and that one is done. It's just that simple. Last one, another C's, H's, and O's. It's a type of combustion, C's, H's, and O's. I'm going to count each side. I see 2, 2, 2 versus 1, 2, 3. First fix the carbons by doubling that, then fix the H's. They're already fixed. Now we have the, once again, we have the 2, 3, odd, even. There's nothing that I can write there on the O2 line that's going to totally fix it. Well, there kind of is, but it's not legal. I can't write 1.5. I'll try it for now, though. But what that means is, see, that would be 1.5 times 2 is 3, and then it would match, but you can't have a half of an O2. And so double everything. I will make this 2 of these, 3 of these, 4 of these, and 2 of these, and that is now balanced. Next one says, just gives you a word thing, so you have to be able to write some formulas. Iron, Fe, burns in air. Wait a minute, which part burns in air? There's no formula for air. We're really talking about O2. It's going to make iron oxide, but not just any iron oxide. I'm going to go over here and just do a little +3, -2. How did I know it's +3? Not because the periodic table told me. That's the one that's a transition metal. It's because that's what the Roman numeral is telling me is the charge of the iron. Crisscross. It's going to take 2 oxygens and 3 of these. Now I have to balance that. If I have 2 oxygens on one side and 3 oxygens on the other, I'm probably going to have to triple this side and double that side to get 6 on each side. But now I have 2 times 2 is 4 irons, so I need a 4 there. Magnesium hydroxide. Let me find some scrap paper to find out what magnesium, let's see, magnesium has a +2 charge. Hydroxide, it's one of them that's not on the nonmetal side like that we'd expect for it to be. It's one of them that's actually on the back side. So hydroxide, which we're starting to understand, is the OH minus. So OH minus 1, it's going to take 2 of those OH is to balance off just one of those magnesiums. Mg, OH taken twice. Reacts with nitric acid. Somebody threw you a bone and gave you the easy one. And it's going to form water, H2O, and magnesium nitrite. Remember, magnesium is a +2. Found that on the front of the chart. Nitrate is a -1. So it's going to take 2 of these, but only 1 of these. So I'll write that as Mg, NO3, but I gotta have 2 of them, so it's in parentheses, taken twice. Once again, balancing these, I'm gonna re-envision my H2O as an H tied to an OH so that I can count things separately. I'm seeing 2 nitrates over there, so I'm gonna double that over there. I'm seeing 2 hydrogens over there, 2 hydroxides over there, so I'm going to double that over there. And that is balanced. Next one is some LOL, OL, some energy charts. First, we have to write the chemical equation. Tell whether it's and whether or not it's exothermic or endothermic. So here we go. C4H10. Burns with air. That's oxygen. Not just air, but oxygen. It's going to tell me, it didn't tell me whether it's, oh, it does tell me the product, CO2 and H2O. That means it is a complete combustion. Step 1, write this. It's going to also tell me that it releases energy. So that, let's see, the products are there for cooking. We know that when we burn it, it's going to give off energy to cook stuff, so we're going to have plus energy. That makes it exothermic because the heat's exiting. We're not putting it in at the beginning, the heat's exiting. Exothermic, said to identify this. Is that balanced? No. I'm going to need at least 4 carbons on this side because there's 4 on this side. I'm going to need at least 5 waters on this side because 5 times 2 is 10 to match the 10 on this side. And when I now count up all the oxygens, I see 13 on the right, but I only see 2 on the left. What can I write here that will fix it? Well, I'm going to just play the game and write 6.5, but ultimately I'm going to have to go back and double everything. I'm going to need 2 times as much as that. I'm going to need 6.5 times 2 is 13 of those. I'm going to need 8 of these, and I'm going to need 10 of these. So, checking out the energy flow. Something to consider is that idea that when we're all done, these things are going to be at room temp. We had some gas that was, I don't know, it wasn't hot yet. But apparently we know that when you're cooking stuff, this is some sort of a gas or some sort of a chemical that has lots of chemical energy. What happens to that chemical energy when we light it? Well, it changes into heat. The ECH goes to E thermal energy, thermal. So when we're all done, it gets really, really hot. And this has much less chemical energy. Where does that heat go? It flows out into the, well, it flows into the meat, it flows into whatever you're cooking, it flows out into the, it definitely goes out of the system. So once it cools back down, we'll have lost a couple of bars of energy. The reactants had a lot of energy. But when we're all done, the products have less energy because it exited. It's an exothermic reaction. The energy flowed away from the system. The next types are simply types of reactions. What are the types we have to deal with? Well, combination, synthesis, oops, those are the same thing. Let me rewrite that. Combination or synthesis are the same type of reaction. It's just different names. You can always tell them they have one and only one product. Decomposition are kind of the opposite of a synthesis. They only have one and only one reactant that breaks apart into simpler things. The next two types to deal with, single replacement. These are usually identified, they usually have, well, they have 4 things total, 2 reactants, 2 products, but what we find is they have a single element on each side. That can be tricky sometimes, because when I say single, it isn't always that it's one atom. Sometimes it's H2 or O2 or Cl2, but it's a single element on both sides. And when I usually say this thing about double replacement, I usually say something like double complicated, double complicated, double complicated. It's 4 ionic substances. It's all double complicated. 4 ionic substances. 2 on the left, 2 on the right. They just switch places, switch dance partners. Look at that first one. Very, 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 very double complicated. 1, 2, 3, 4 ionic substances. Double replacement. The next one has a single element here and a single element here. It's kicking out the, whoops, wrong one. The magnesium kicks out the iron and makes iron dance alone. That is a single replacement element on each side. One that I didn't put up there, I should have talked about the idea that there's also the combustions. What are the combustions? They have lots of C's, H's, and O's. So they end up, there's complete and incomplete. Complete and incomplete. Both of them start with hydrocarbons, some sort of fuel made of C's and H's and usually sometimes some O's. Both of them start with hydrocarbons. But the complete end with carbon dioxide and water, and the incomplete only end with carbon monoxide and water. This is C's and H's and O. And so it's definitely a combustion, but since it's CO2, it's complete combustion. Next one. I see one and only one reactant. That has to be a decomp. Decomposition. Next one, and lots of C's and H's and O's. I see a fuel on one side, oxygen. In fact, it's just like 33, except carbon monoxide. So we have incomplete combustion. And finally, if I only see one product, that is a combination or synthesis. That ends page 2.